Okay, so let's start probably with okay, so with homework probably with homework problems first. Okay, so this problem number 20. Let's start with this one from the homework assignment. So probably many people have done that problem, but yeah. So problem number 20 is a circuit that contains several capacitors, and we have to figure out what is the equivalent capacitance of that. And look, in this problem, you don't have any, at least I don't see any other choice, but start by combining those three capacitors right here. They're connected in series. And I don't see other way of doing it. So let's figure that out. So everything is in microfarads, and for my version of the problem, capacitor C1 is 14 microfarads. Okay, so look what happens. You replace all those three capacitors with a single capacitor, and we have to find its capacitance. So you have, let's start with the circuit like this. You have this capacitor that is 5. Everything is in microfarads, so I'm not going to put the units, just the number of microfarads. So those three are going to be combined with a single capacitor, and we have to find its capacitance. After that, you have, what do you have? Well, after that, you have this capacitor C1, maybe. For me, C1 is 14, we said. Oh, no, this is C2. C2 is 8. C2 is 8. Okay, and let's not forget that we have one more capacitor in the middle, that is 4. So this one is 4. Now we have to figure out the effective capacitance of this one, those three connected. And you figure out its effective capacitance by saying that the inverse of the effective capacitance is equal to the sum of the inverses. So it is equal to 1/24 plus. So for me, C1 is 14, so it is 1 divided by 14 plus 1 divided by 8. So, well, I cannot do this arithmetic without a calculator, but you just add those and the effective is going, the addition is going to give you the inverse of the effective capacitor, so you have to find the inverse of that number that you have. And if you give me the number,
0.238.
0.338.
238.
238, okay, like this.
Yes.
So this is the effective capacitance, not the inverse of it. So, right? When you add those fractions, you get the inverse. What is this correct? Let's make sure that.
So yeah, I think that is the inverse.
Oh, this is the inverse.
Yeah.
Okay, so now your calculator should be able to immediately say the inverse of this number.
4.2.
4.2. One more digit, please. One more.
That's all it has.
Oh.
0.
Oh, okay. Okay, microfarads. Okay, so this is 4.2. Well, after that, it becomes easier because those two are connected in parallel and their effective capacitance is just the sum. So this circuit becomes equal to a circuit that looks like this. Here is your 5. Here is 4, and 4.2 gives you 8.2. And after that, you have another one that is, for my version, it is 8. And that's it. And now again, we have to find the effective capacitance of 3 capacitors that are connected in series. So again, you use the same formula. So now you have 1 over CS prime, let's say, is equal to 1/5 plus 1 divided by 8.2 plus 1 divided by 8. So again, we have to do the arithmetic. But you have to do it. I should have had a calculator with me, but I don't. Okay, so when you add them up and find the inverse, the answer should be 2.24. Do you get the answer or not? So add them up, find the inverse, and the answer should be 2.24. Is this okay or not? Okay, so this is how you handle those type of problems. So before we go to other problems from other sources, do you have questions about the homework assignment that is due tonight? Yeah.
Number 18.
Okay, let's look at number 18. Okay, so this is a similar problem, but it is with resistors. And for problem number 18, you have exactly, you're going to have, on the test, you're going to have questions of this type, the type of problem 20, of this type, the type of problem 18. So, and they're not difficult. Once you figure out how to do them, they're not difficult.
Will they be through response or will they be on the multiple choice?
I don't know. I have to write the.
You should make it on through response.
Well, Yeah, well,
Just an idea.
we'll see. Well, I'm probably going to work on the test on Thursday evening, so. Okay, so problem number 18 from the homework assignment. So again, look how to simplify this. So you can immediately combine this 6 ohm with this, with R2, which for me is 15 ohms, and you can replace them with a single resistor. Those two, a single resistor that is a sum of 6 and 15. So once you do that, the circuit looks like this. You have, this is R1, this is R1. After that, when you combine those two, and I'm going to draw them somewhere here. So the combination is going to be 15 plus 6, 15 plus 6, 21 ohm. And what do you have after that? You have this. Which is 20 ohm. And you have this combination of two like this, with 9 and R3. 9 here, this one is R3. So R1 for me is 8. R3 for my version is 12. 12 ohms. So look, strictly speaking, those three are connected in parallel. And you can replace them with a single capacitor with equivalent capacitance that you can calculate. Or if you want, first those two in parallel and after that a third one, but it is easier, just those three. Look, those three are under the same voltage, so they're in parallel, there is no any. So when you replace them, when you replace those three with a single resistor, you're going to have a circuit that looks like this. You have your 8 ohm here. After that, those three replaced by a single resistor that we're going to calculate its resistance. And after that, you have your 20 ohm, and that's it. So let's figure out what is the resistance of those three. So 1 divided by R parallel is going to be equal to 1/9 plus 1/12 plus 1/21, like this. 1 divided by 21. So again, you have to add the fractions. The result is going to be the inverse of the equivalent resistance. So can you tell me what is R parallel here? Okay, 4.13 tons. Okay. So this one becomes 4.13. And now when you add 8 plus 4.13 plus 20, you're going to get 32.13.
You drew it wrong, because you should combine the 8 and the 4.13, but then that will be in parallel to the 20. They won't all be in series.
The 20 is not there. The 20 is here, right? So the 20 is right here. So the 20 is right here. Right here. Okay, thank you. So you have, now let's see. Well, now careful. First, you have to combine those two. So when you combine those two, you're going to get something that looks like this. You have those two are going to give you a single with resistance 12.13 ohms. And you have the 20 like this. So this is 20. So now the equivalent resistance of those two is going to be, so the equivalent resistance is going to be R parallel is equal to the product 20 multiplied by 12.13 divided by the sum 20 plus 12.13. So this is, what is it?
7.5.
Yeah,
7.5.
yeah, the answer should be, yeah. Okay. So, yeah,
So whenever you have more than two resistors in parallel, you can add them together with the inverse, but if it's just two, you have to do.
yeah, when it is just two, this is easier, right?
Okay.
It is easier. This is the same thing as 1 over R parallel equal to 1 divided by 20 plus 1 divided by 12.13. It is the same thing, but it is faster to do it that way. Okay. Questions? Okay, other questions from the homework that is due tonight? If not, let's go to practice test. So let's go to practice test, problem number. Problem number 18. Problem number 18. Okay, so let's look at problem number 18 from the practice test. So 18 on the practice test. So you have the circuit. You want to figure out, of course, first the equivalent resistance. They're asking about the equivalent resistance. So look, you have part A, find the equivalent resistance, and you find it by combining the 60 and the 30 ohm as a single resistor. And the result of this combination is going to be 60 multiplied by 30 divided by 60, 60 plus 30. So this is 1800 divided by 90 is equal to 2, what is it? 20 ohms. So this is 20. And therefore, the equivalent resistance between points A and B has to be 30. Okay. So part A is 30. What is the potential drop across the 10 ohm resistor? So they say that the potential difference between points A and B is 30 volts. So V is equal to 30 volts. it is as if you have a battery that is 30-volt battery connected like this. But it doesn't. You only need to know the potential difference. So look how to figure that out. They want the potential difference here. For part B, they want the potential difference V prime. V prime, right, between those 2 points. And you use Ohm's law. So you have to find the current in this circuit. So the current is going to be, the current in the circuit is going to be the total resistance, the voltage divided by the total resistance, right? Which is 30 divided by 30 is 1 ampere. 1 ampere is the current, and therefore the voltage V prime is going to be the current multiplied by the resistance R. So it is going to be the current is 1 multiplied by 10 gives you 10 volts voltage V prime. Is it clear or not? So for part B, you go through, you find the current, and using the current, you can find the potential drop across that resistor. Okay. Part C. So part C, you can answer without calculations. Because look, you found that this potential drop is 10 volts. The total potential is 30. So the potential difference between those 2 points here is 20. Because this plus this has to give you the total voltage.
But wouldn't that be the potential drops of 60 and 30 combined?
Yes, but it is the same because look, the potential here is the same as the potential here because those points are connected with wires, and the wires transmit the potential with no change. So this is the same thing as this and this and this. Everywhere the potential difference is the same. Points are connected with wires. The potential of any point connected with another point with a wire is exactly the same. Metals are equipotential surfaces. So the answer for part C is directly with no, just looking at the diagram. Right? And now look, part D follows immediately. Because if this is 20 volts, the current has to be the voltage V prime or what V double prime. So this is V double prime divided by the resistance of 30 ohms. So it is going to be 20 divided by 30, which is 0.66. Right? You see that it looks complicated, but if you grasp the idea about equipotential surfaces, about Ohm's law, and this is why actually this problem is given. You to you to exercise the ideas. Okay. Uh,
Going back to part B, I mean, in a situation like this, are you always gonna end up, I guess they gave you the voltage of 30, huh?
yeah.
Never mind, that was just a happy coincidence that it came out to be 1 ampere.
Oh, yeah. Well, so you can calculate without using a calculator. So practically, this problem doesn't require a calculator. And yeah. And look, they don't show the battery of 30 volts, but you can imagine it. It is, if you want, if you feel like. Yeah.
Can we do number 4?
From the practice test? Okay, problem number 4 from the practice test. Oh, it is an exercise about flux, right? So we're going to use the concept of flux when we deal with magnetism also. So even though I'm, okay. So problem number 4 from the practice test. So you have a surface uniform electric field, the way it is shown on the diagram. They give you the size of this cube. Electric field passes through from the left. What is the total electric flux that passes through the Gaussian surface? Look, the surface is here. Clearly, there is no any flux through this side or through the bottom or to the front or from the back. The only flux is here and here. But whatever comes in gets out. The total flux has to be 0 because once you take it with positive sign, a second time with negative sign, and it goes away. The flux should be 0 here. Right? It is, again, no calculation needed. Well, yeah.
Let's say like you were to have a sphere, how would you then like know?
Oh, well, that's a good
Would it be
question.
0 as well?
It
Because
just, yeah, it will be 0 again, but you cannot prove it without using some math that is beyond. But you can say that if it is a sphere or any other shape, closed surface, since there is no any electric charges inside, the total flux has to be 0 because Gauss's law says that the flux is equal to the total charge inside divided by some number, fixed number. So total charge inside is 0. They have to tell you, oh, no charges inside this tube or this sphere or this ball or whatever shape you have there. And this immediately is going to tell you, if no charges inside, the flux must be 0, no matter the shape. So,
could you explain number 2?
number 2. So, 3 identical spheres, metal spheres. One, the first, okay, so look, everything is in microcoulombs. The spheres are identical, and they say that the charge on the first sphere is -2 microcoulombs. They say that the charge on sphere B is what is it? B is -6, and on sphere C, it is +5. So first you touch A and B, and they separate them. So look what happens when you touch two identical metal spheres. They're going to divide the total charge equally between themselves because they're identical. So the total charge is -8 divided equally to 2. They are going to give you -4 and -4. Okay. So this is the first step. After that, you touch B and C. So after that, you touch B and C. So now you have this and this. Again, +5, -4, the total is +1. And they have to share this +1 equally. In other words, the result is going to be +0.5 and +0.5. For those two. And they're asking, does sphere C ends up with excess or deficiency? Well, it is positively charged, therefore it has a deficiency of electrons. How many electrons deficiency? Well, you have now QC now is equal to 0.5 microcoulombs. The number of electrons is going to be 0.5 times 10 to the -6, divided by the charge of one electron, one elementary charge, which is 1.6 times 10 to the -19, one elementary charge. And when you do this division, you're going to get a large number of electrons of the order of trillion electrons, or 100 billion or so. So this is approximately equal to 0.3 times 10 to the 13, which is 0. 3 points.
That's it, yeah.
Yeah, that should do that. Yeah.
Could we do number 12?
Okay, number 12 now. Problem number 12 from the practice test. So conducting solids, conducting sphere with given radius has an excess charge. This sphere is located at the center of a hollow sphere with radius B and outer radius C. Also with excess charge of +6. So let's draw the diagram and see how it works. So you have here is the large sphere with radius A, and oh no, it is inside. So you have another one that is like bigger like this. And it's bigger, and it has human thickness also. Something like this. So let's see the numbers. This one, the inside sphere is with radius A, and the large sphere, inner radius B. So this from here to here is B, and from here to here is C, like this, okay? And this, of course, is solid. So all of it has to be solid like this. So the solid one that is inside is +6. So this +6, of course, is going to be on the surface. All of those charges, excess positive charges, reside on the surface of this small sphere. But now look what happens. You want the total charge on the outer sphere to be +6, the total one. But this outer sphere, this spherical shell, has outer surface and inner surface. For the inner surface, you must have -6 on the inner surface. Why? Well, you can think in terms of Gauss's law, or you can think in terms of induction. So this +6 attracts -6 in such a way that to make sure that inside the shell, this large spherical shell, there is no electric field, right? Inside metals, the electric field is 0, and you can make it 0 only if you cancel out this +6. So -6 has to be on the inner surface. The outer surface now doesn't have any other choice, but it must have +12. So that the net charge on the large spherical shell to be +6 as the problem requires. So, they have a hint here, use Gauss's law. Look how you use Gauss's law. Let's make this more thicker so we can see better the diagram. So look how you use Gauss's law. Imagine a Gaussian sphere with center at the center of the system and radius in the middle, in the bulk of this metal. So this, imagine a Gaussian sphere imaginary Gaussian sphere that looks like this. Somewhere inside the metal. Well, the electric flux that goes through this Gaussian sphere, through this red imaginary Gaussian sphere, must be zero because we know that in metals, the electric field is zero. So electric field at any point of this red sphere is zero. Therefore, the flux is zero. So flux, the red flux is zero. Red flux is zero because the electric field everywhere, this red sphere is inside the metal. Inside the metal's electric field must be zero. But you know that that flux also, according to Gauss's law, should be equal to the total charge inside that red imaginary Gaussian surface divided by epsilon naught. Right? This is Gauss's law. This means that Q total inside this red sphere is zero. But look, you have 6 here. Therefore, you must have -6 on the inner surface of the spherical metal shell in order to have a total 0. And that's it. Once you have -6 on the inner surface, the outer surface must have 12, so that the net charge on the spherical shell to be, on the large spherical shell, to be +6, as the problem says. Does it make sense or not? So here we apply Gauss's law. Yeah.
So with Gauss's law, and you were doing Q total equals 0, since you know that you're saying that since the inner circle is 6, that means the inner part of the outer circle would have to be negative to equal 0.
That's correct.
Okay.
So you'd have +6 -6 to be 0. So total inside the red to be 0.
Is it the last sentence where it says the hollow sphere also carries a total excess charge of +6? Is that how it equals 12?
Yes,
It's that.
yes.
excess.
So you want whatever is here plus whatever is here to be equal to 12. We established that this must be -6.
So it must be positive.
So this has to be +12 so that the net on the entire large sphere to be +6.
Number 17.
Okay, problem number 17 from the practice test. Problem number 17 from the practice test. And by the way, the shape here of those spherical shapes, I could have drawn any shape. It doesn't need to be spheres. Gauss's law holds for any shape. So problem number 17 from the practice test. You have light bulbs connected in parallel. 120 volts Is it a battery or is it a AC? Doesn't matter here, I guess. They say that each bulb dissipates average power of 60 watts. And there is a fuse when you exceed the current of 9 amperes. What is the largest number of bulbs which can be used in this circuit without burning the phase, the fuse? Well, look, let's say that you have N, but let's figure out. So look, first, let's figure out the resistance of each light bulb. Well, the voltage applied to every light bulb is 120. It uses 60 watts. So you say this, the power of one bulb is 60 watts. The voltage applied to one bulb is 120 volts. Remember, one of the formulas for calculating the power is voltage squared divided by resistance. It follows that the resistance is equal to voltage squared divided by power. So this is 120 squared divided by 60. And you have to do the arithmetic, or maybe I should do it. So this is 2 times 120 is 240, right? 120 squared divided by 60 is 240, right? Okay. So the resistance of one light bulb is 240. So now you have N 240 resistors. 1, 2, 3, 4. N of them. The equivalent resistance has an inverse equal to the sum of the inverses. So you have 1 over 240 plus 1 over 240 plus and so on, n times, right? You have to add. So this is equal to n divided by 240. And we're looking for n here, right? So from this, you conclude that the resistance, the equivalent resistance are parallel, should be 240 divided by n ohms. In other words, the circuit looks like this. A single resistor with resistance 240 divided by n, connected with this fuse and connected to 120 volts. Well, battery. Okay, let's make it battery. This. So now the current in this circuit is going to be the voltage divided by the resistance. In this case, it is the resistance are parallel. And you want this to have the maximum value of 9 amperes. In other words, your equation looks like this. 9 is equal to 120 divided by 240 divided by n. And this is 240 divided by, so that's. In other words, 9 is equal to n times 120 divided by 240. In other words, n, well, you can cancel if you want, this is 2, and therefore n is equal to 9 times 2, 18. So if you put 18 light bulbs, the fuse is going to burn. Therefore, you have to stay below 18 light bulbs. So I don't know if they gave the answer to be 18 or 17, but 18 is on the verge of triggering the circuit breaker.
It says 17.
Yeah, so one less than 18 then is safe.
You've done something like this in the past, but could you help us remember how to do number 14? It's the one where there's two electric charges opposite of each other.
Oh, yeah. Oh, okay. 14, problem number 14. Problem number 14. So you have point charges in a rectangular arrangement. They give you the geometry of the setup. They wanted to figure out first the potential at corner A. To find the difference, you have to find the potential at corner B. And after that, energy if you place a charge at corner A. Okay, so so let's start with the diagram. So you have -5 microcoulombs here. And after that, here is point A, and here is point B, and this is +2 microcoulombs here. First, find the potential at point A. And look, the potential at point A is generated by this and by this. And that potential, the formula for potential is generated by a single point-like charge is the constant of proportionality times the value of the charge together with its algebraic sign divided by the distance from the charge. So they say that this is 0.15 meters. This one is 0.05 meters. So the potential at point A is going to be, well, the part that is generated by the -5 is going to be K times -5 divided by this distance, 0.15. And the part that is generated from the positive 2 is going to be k times positive 2 divided by 0.15. So 0.5, 0.05 is the distance, 0.05.
Do you need to change the -5 and +2 to coulombs since they're microcoulombs?
Yeah, we have to do it. We have to do this. So those are microcoulombs, so this is 10 to the negative, right? Everything. Which again, you can simplify. VA is going to be equal to k times 10 to the -6 times, well, -5 divided by 0.15 and 2 divided by 0.05. So you can make this equal to k times 10 to the -6 and 3, 6. This is going to 1 divided by 0.15. And here you have to calculate and you have to get the value of the constant k from the formula sheet. It is of the order of 10 to the 9th. Let me see.
Is it 9 times 10 to the 9?
Yeah, 8.99 times 10 to the 9. So this is going to be, well, calculated. This is calculated. And if you give me the number, that will be useful.
It's 6,666.67. I don't know.
Okay, 6,000.
They have 6 times 10 to the 4.
So use more significant digits, maybe. 6 times 10 to the 4 volts. That's it, right? What is the answer?
You got 59,933.
Did you do this? I don't know. You have to use a calculator here.
I was outvoted. They said 59,000.
Okay. Say it again.
59,933.
59,933
Yeah. 33.
volts. Point.
Three.
So if it's not, yeah, well, 43. Okay.
So that's
Yeah, it's possible. Yeah. So this is part A of this problem, right? This is part A of the problem. Part B, do the same thing, but now find the potential at point B, and after that you have to find the potential difference. So this voltage VA is a positive number. So we have to keep track of the algebraic signs. So for part B, you do this a similar calculation. So the voltage at part B is going to be equal to the contribution from -5 is going to be k times -5 divided by the distance 0.05. And the contribution from the +2 is going to be k times +2 divided by 0.15. All of this times 10 to the -6. So if you want, yeah, all of this times 10 to the negative 6. So this is going to give you 13 divided by 0.15 times k times 10 to the negative 6. Well, you have to find the number. But it is going to be a negative number. So put a negative sign, that's important.
Negative 779,133.
779,133. 133. Okay, but negative entities involved, of course. And sorry, B minus A. So BB minus BA is going to be negative 779,133, negative 59933 is going to give you negative something that you have to calculate. And hopefully this is the answer for part B. Part B. So something like 840,000 or so.
Negative 8.
Yeah.
83.
Yeah.
8.39.
Yeah. But negative, right?
Negative.
Yeah. And so now we're ready to answer part C. What is the electric potential energy of a positive 3 microcoulombs at corner A? Well, at corner A, we have the voltage at corner A. And you say that the electric potential energy is going to be equal to the value of the charge together with its algebraic sign times the voltage at the point where the charge is located. So it is going to be positive 3 times 10 to the negative 6. VA is 59933. And that's it, right? This should be the product. So the voltage is positive at that point, the charge is positive, the electric potential energy is going to come to be a positive number. So this is part C. Yeah.
Could you just explain again real quick how you got negative 13?
Oh, I added this plus this. So you add by multiplying numerator and denominator by 3 in order to get the same denominator like here. So 3 times 15, 3 times 5 is 15 with negative sign, plus 2 is negative 13, right?
Okay. Yeah.
Just fractions. You can use your calculator. At the end, it should work. Okay. Okay, other questions? Other questions? Are we done? Okay, so tomorrow we have a class. If you encounter some other issue, let me know tomorrow in class. But the plan for tomorrow is to start chapter 21, which magnetism. Yeah.
You said that we'll have a question on problem number 19 from the homework that will definitely be on the test.
Problem 19 was discharging a capacitor through a resistor, right?
There's Kirchhoff's junction rule.
Oh, yes, you're going to have Kirchhoff rule. So you're going to have some circuit with that you don't have other choice, but you have to use Kirchhoff rules.
Okay.
So it is, and again, most of the points for that problem are going to be in writing the system of equations correctly.
Are there any other problems that we should look at?
I promised to put a problem like one of the homework problems had a circuit which
I think it was number 13.
yeah, a resistor, let's figure it out, a resistor and capacitor, and you were charging.
Right. And you use the equation, it's the
Yeah, so you have a standard exponential,
Q naught
Mhm.
1 minus e to the negative t over rc.
yeah, so it was problem number,
13, I think.
yes, it was problem number 13, yes. But keep in mind that, let's say, the same type of question would be if instead of charging, you discharge, you don't have a battery, the capacitor is charged, and you close the circuit, and it starts discharging exponentially, and you have the same idea there, right? So just make, so, well, this problem requires you to be comfortable with logarithms, right? This is, but this should, so I promised to put this type of problems.
Are these all the only equations you're gonna give us? Because I noticed that there's none regarding power. Or
Well, you know, sometimes I just forget to put all the equations that are needed. And in that case, you have to tell me that some equation is missing and I'll put it on the board. But, well, yes.
Okay. Practice test problems that you should get.
On the practice test, well, the practice test is because I'm going to use the practice test as a source, but which problem exactly? Which problem exactly is? Here it is on the practice test. You have, for example, a problem that requires Kirchhoff rule, right? This type of problem. So it's not going to be exactly the same number of ohms and exactly the same, but it is going to be this type of problem. So if you practice solving this problem, you should be able to do the, yeah.
Did you add that one later? Because I just printed out the practice test. I don't have a number 21.
Really?
I have it.
That's all.
I'm surprised. So
That
what?
might have been my mistake then.
So I emailed a PDF version, and I'm looking now at Microsoft Word, but they should be identical because.
I got the one off of WebAssign. Would there be a difference between those two?
The one he emailed.
Okay.
So WebAssign may have cut the last page. I don't know. I'm surprised at this, but
Okay.
it is a problem of the type that we said that we're going to see.
Okay.
Right, yes.
So for the conceptual type of questions, would you suggest just going back to the homework then?
For the conceptual, do the homework, and also I send those quizzes also. Go over them. Those quiz questions, we did some of the questions in class, and some of them we didn't have time to do in class, but the answers are given. Make sense of them. If some answer doesn't make complete sense, tomorrow we have a class, let's talk. Okay. Well, let's end it for today, and tomorrow we're going to continue with the rest.
Is it also 15-minute, like our normal exams, like last semester?
You should be able to finish in 20 minutes.
Okay, so like last
Yes,
semester.
yes. But look, I have difficulties finding proctors. The department kind of doesn't have the resources. So proctoring is going to be probably either just myself and maybe one person if I can find. So you have to collect all the questions that you have and try to get the answers in one ask rather than, right? So just be ready to, because the class is what we have about 75 people in the class, a single person. But again, except this Kirchhoff rules type of problems, the other problems you see that they practically don't even require a calculator. Many of the problems didn't require calculator. So you shouldn't look for something completely long, complicated. You just have to have the ideas, the approach, the right approach. And the rest is algebra.
And you said that the people that have the 1 o'clock class should try coming out.
Yes, please. If you can do that, that will be great. If you cannot, because at 1 o'clock I have to do a test for people that are online, registered for the online class. And it will be difficult to do both Zoom, and if I have too many people that are in class, it's going to be a struggle too. But if you don't have other option, come at 1 o'clock. 11 o'clock is preferable if you can make it.
How is the online thing going to be set up?
Oh, so for the online people, you have to, if you're not registered for the online class, you have to give me your email, your name, and I'm going to email the problems, let's say 10 minutes before 1 o'clock. And you have to turn on Zoom, and you have to be on Zoom with the camera on, work on the problems, and when the time is up, you have to make a copy of your work as a single PDF file, email it to me, and that will be it.
So I'm technically actually signed for online and I've been coming for 11 o'clock.
If you can come at 11, that would be great. You don't have to do it by Zoom.
Okay.
If you're here in class, you can ask questions, ask for help, hints, and it's good, but up to you.
All right, awesome. Thank you.
Welcome.